everyone. I want to talk about transformations of exponential functions. So let's get right into it. Up on the top, I have a transformation of an exponential function. So now this is a transformation of its parent function, which we talked about earlier was f of x equals b to the power of x. Okay, now depending on what b is it decay or growth? All right. Doesn't matter, but the function itself is f of x is equal to b to the power of x. Okay, so now what happens if this b to the power of x is kind of manipulated, right? That's basically what transformations are, a manipulation of the original function, which we call the parent function. So here I have a times b to the power of x minus h plus k. All right, so what does the a mean? What does the h mean? What does the k mean? Because right now, all we know that looks normal so far is this b to the power of x. That's what's familiar to us. Right now, the manipulations come in a, h, and k. So let's start first. Let's go from left to right, I guess. Let's start with what a means. Well, if a is less than 0, then we have the graph is reflected about the x-axis. So it's reflected about x-axis. Alright, so there's a reflection. Now, what if a is greater than 0? Alright, if it's positive. Alright, but here's what happens. So if a is positive, a greater than 0, something happens here. Alright, so let's make some bullet points. Alright, so if the absolute value of a is greater than 1, okay, so we have to take the absolute value in consideration here because a number of things can happen if a is greater than 0. Alright, because we also have to consider that when b is, what happens, I'm sorry, not b. Okay, when b is in between 0 and 1 and when b is greater than 1, something happens. So something similar happens to the a. So when a is greater than 1, we have, this is a stretch, a vertical stretch. Now if a is in between 0 and 1, we have a vertical compression. So vertical stretch, you can think of it as like a rubber band stretch. Compression means that it's being like compressed, right? They're coming in together. It's like, think of like two walls and they're coming together, moving walls like in the movies. They're coming together and they're going to squish the person. That's vertical compression. Okay, so this is a is greater than 0. Okay, so this is all about the a. So here was our a. Well, let's go ahead and call it a. Now what happens if h is being manipulated, all right? What's the h doing to my x, right? So key thing is that it's being minus h, all right? So if h is positive, then x minus h will stay as it is. So if h is positive, right, basically meaning x minus h is staying the same, then you are moving h units right. Alright, so this is like a shift to the right. Now if h is less than 0, I'm going to take the absolute value of h, and the reason why I'm putting it in absolute value is because that's how many units I'm going to move to the left. Okay, so this is h, and now let's talk about k. Right. K, one of my favorites, because it's easy to see it, right? If what I'm adding to the whole function and what I'm subtracting from the whole function, because it depends what k is positive or negative. All right, so if k is positive, because it's basically, well, I don't want to say it's your y-intercept in this case. All right, we have to look at some examples and then you'll see. So k units up, so if k is positive, then I'm going k units up. Now if k is less than 0, again, put that in absolute value because that's how many units I'm going to count, down. Right, so this is a shift down and up. So k is the up and down shift, h is the right and left shift, a is the reflection, and it's a vertical stretch or a vertical compression. I want to do an example of an exponential function that has these transformations. So now let's say, I'll write it up here, f of x is equal to -4, and then we have times 3/5, which is raised to the power of x plus 4, and the whole function is added to 3. Alright, so let's do an analysis. So here's our analysis of this function here. Well, my a is equal to -4. Alright, so I can say that, well, a is already less than 0, so we have a reflection about the x-axis. We have this down. Okay, also the absolute value of a is equal to the absolute value of, so we have -4. Wow, that is absolutely hideous. Okay. We have the absolute value of -4, which is 4. And then, so we have this is the absolute value of a, which is 4, is greater than 1. So I have a vertical stretch as well. So I'm stretching my graph. Now these are the manipulations that happen to the parent graph. All right, we saw the parent graph in the previous video. So let's put an analysis of this first, and then I will compare the two graphs together, the parent and our new function. So we have a vertical stretch. Alright, and then let's take a look at our b, just for the sake of it. So b, in this case, is equal to 3/5, and 3/5, this is less than 1, alright, but greater than 0. Okay, so I am looking at a decreasing, so I'm looking at exponential decay. We have exponential decay here. And then we have an h. Our h, alright, you see, now what I was talking about earlier, the x minus h, you see here we have x plus 4. It's not in the x minus h form. So this means what you have is x minus h, alright, basically meaning that your h is a negative number. So h is equal to -4 in this instance, and that's how they have x plus 4. Alright, so if h is equal to -4, h is less than 0. So this means I am moving 4 units. I take the absolute value of -4, so I'm moving 4 units to the left. Okay, and then, what else do we have? We have k is equal to +3. So I am moving 3 units up. It's already positive, so I'm moving 3 units up. Okay, so this is the analysis of our exponential function. Okay, so I've placed the two functions together. On our left, we have our parent function. On our right, we have our transformed function. Alright, so our parent function, 3/5 to the power of x, this is what we have, this is what we expected. Alright, next, a normal exponential decay. On our transformed function, you see it's much different than what we have from our parent, because we've, of course, I guess you could say we mutated it. Alright, because we have -4, so it's negative, and it got reflected about the x-axis. So, you can see here, right, we have our x-axis here. And it got reflected. This one has a vertical stretch, as opposed to the parent function. Right, I kind of stretched it out. And our h was -4, so we shifted 4 units to the left. So here was our shift to the left, 4 units left, and then finally we moved it up 3 units. Okay, so these were the transformations that took place between the parent and the transformed. Okay,